This section will talk about the Vfd selection, part B. So before we select the VFD, the drive, we should select the mode first. So typically we will select the mode according to the load type, load curve. Here is an example. The load is pump, and the pump is rated speed is 2000 RPM, and rated power is 150 kilowatt. And according to the formula, we can get the torque of the pump from the kilowatt and RPM. Then we get the torque, rated torque of the pump. And here is the curves. This is the frequency. For example, 50 Hertz is here. For most of the motors, the rated is 50 Hertz. Here we also use this as example. Sometimes, the motor will have the 6 Hertz, or even special like 80 Hertz, 120. So here we use a 50 as a reference, as example. And for example, for the two-pole motor, the cycle speed is 3000 RPM. For four-pole motor is 1500 RPM, and the frequency is 50 Hertz. So choice one, we use two-pole motors. This one, two-pole motor, cycle speed is 2000 RPM, and the rated speed of the pump is 2000 RPM. So here is the 2000 RPM. So two-pole motor, 2000 is like here, 2000 RPM. So the load curve is here, rated 2000 RPM, and the torque is here. So for the motor, 50 Hertz is rated. Above 50 Hertz is the constant power. Below 50 Hertz is constant torque. But actually, as we discussed before, because of the coaxial fan cooling decrease with the speed, so the actually torque output will also decrease. So the curve will be right here for the particular motor. So here we can see, at this point, the torque is for the pump is 1716. But here you can see the output of the motor torque is about 95% of the rated. So that means, the maximum torque, the rate torque of the motor should be 7160 divided by 95. This is the rated torque of the motor. This torque. So we have the torque, we have the rated speed of the motor as 3000 RPM. Then we get the rated power of the motor. Torque, speed, we get the power. So for the standard motor will be 250, a little bit higher than the calculated data. So the second choice will be use a four-pulse motor. Four-pulse motor cycle speed is 1500 RPM. So for the pump speed is 2000, it would be like here. So this point is 2000 RPM for four-pole motors. And you can see at this point, the torque is about 75%. Because this area is we call the constant power. Constant power. For example, here the speed is 2000 RPM. But the rated is 1500 RPM. So then we have the 70% of the torque basing on the rated, because of the constant power. So the torque at this speed will be 75%. Then, this data is 7160. 716, then we get the rated torque of the motor, 955. Same, we have the torque, the speed, and we get the power. So the standard motor is 160 kilowatt. Here you can see, the rated torque, rated power for the four-pole motor. If we choose four-pole motor, the rated power will be less than the two-pole motor. So the reason, for the two-pole motor, the rated point for the load here is the area for the constant power. We utilize the area of the constant power. So like we don't have so many waste, for the motor power. So it's better to use flux weakening or constant power area to make sure, the rated power of the selected motor will be minimized. Or we can say, try to run the motor above the signal speed. Then you can get the minimum power rating for the motor. But special requirement is this motor should be run higher than the rated frequency. Like here, you need to run about 66 hertz for the rated, above the 50 hertz rated. Uh, if we choose the two-pole motor is here. The torque is here, but the speed, rated speed here for the load, but the rated speed for the motor is here. So actually we waste, the area with the torque and the speed, the square, represent the power. So actually, the working point for the pump is here, and the actual, the maximum power needed for the pump is like this area. But the most rated point is here. So the motor power will be like here. So the difference of the area, represents the waste of the motor rating. Okay. Another example, the load extruder. Extruder means constant torque load. And the speed range for the extruder, the power, same we can get the torque from the power and the rated speed. Here's the torque for the extruder. Same, this is a motor, 50 hertz, constant power, constant torque. Actually, with the rated torque. And the 50 hertz is here. Okay, if we choose the photo motor is here, and the 50 hertz is 1500 RPM. So the speed is 300 from 300 to 100. Then will be 300 here, 1200 here. So then we get the line one. This one is a working area for the extruder. So now we can see, the torque is like the motor torque is like 80% of the rated. So we can get the rated torque of the motor. Same, we can get the power rating 75 kilowatt. 75 kilowatt motor. If we use 4-pole motor, a 6-pole motor, and here a 6-pole motor, speed from 300 here to 1200 here. Then, the curve is this one, curve 2, line 2. Line 2 is about 80.84, 84%. And then we get the torque, rated torque. And also we get the power, speed, torque, the power reading. Same, if we use the 6-pole motor and try to run the motor with the constant power range of flux weakening area, the selected motor size will be less than the 4-pole motor, from 75 kilowatt to 55 kilowatt. Also, we need to remember, the motor poles is different. This is a low speed motor. This is a high speed motor. This is a low speed motor. And this motor we always run below the rated speed. But this one, should be higher than the rated speed, higher than the 50 hertz, so higher than the rated frequency. Okay. So after we select the motor, then we will select the drive. So there are two critical data for the drive. One is the voltage. So typically the voltage of the drive should be higher than voltage of the motor. If there is a long motor cable, like for the ESP pump, you need to take the loss on the cable count, then the drive voltage will be a little bit higher than the motor maximum motor voltage. So typically, the drive voltage rating is the same as the motor voltage rating. And for the current, you can get the current from this formula: power, voltage, cosine phi, and efficiency. Then you get the current for the drive. For example, motor rating, uh, voltage, power factor, efficiency. Then you get the current. So the current of the drive always be higher than the current of the motor. So if there is some kind of overload, then the select the current of drive should be higher than the motor voltage. Now, typically for most of the drive itself, have the ability for overload, say 120%, one minimum, 1 minute. Some drive, we call it a heavy duty drive will have a 150% overload in 1 minute, every 10 minutes typically. Or even we have a special design for the high overload factor. And also, for the motor, as we said before, the rate the rated power of the motor is kW, the power on the mechanical on the shaft, mechanical power, not the electrical power for the motor. Is the output mechanical power. But for the drive, normally we will define the drive as a capacitor, kVA. kVA is like this, kVA, voltage and current. Okay. So we cannot say the how many kilowatt of drive, but we can say how many kVA, because you have the voltage, your current, then you get a kVA. But the how many kilowatt, this is different from the different motor. The kW is the output of the motor power. So there is some relationship between the drive output kVA and the motor kilowatt power. Drive output kVA is same as a motor input kVA. So different between the kVA is here. This is kVA. Then we have the cosine phi and the efficiency to get kW, the mechanical power. And overload we told before. And the another is we call the dynamic acceleration. That means when we size the motor or size the drive, we need to look at the dynamic acceleration. For example, this is the formula: load torque, change rate of speed. So here is the load torque. So sometimes you have a very large initial moment for the load, and you have a high accelerating rate. You need to faster ramp up for the load. Then this data will be very big. So that means when you size the rating of the drive and the motor, the rated torque or rated power of the motor will be much higher than the load torque, the load power. So this is a very critical issue we need to take into account, especially for the load with high inertia, and you have the requirement for the starting time. Okay, here is example for the Vfd selection. For example, this is NC is represented like Nanco company. HVVF is the medium voltage drive. A here is the input voltage, 6 kV or 10 kV or higher. B is output voltage, kV, and C here. So for most of the air cooling drive, we will use kilowatt. And for the water cooling drive, we use kVA. Okay, also we have a definition for soft starter. So actually kVA is the accurate definition of the rating of the drive, because you have voltage, for example, 6 kV or 10 kV, and then you have a kVA, then you can get the current. you can get the current reading of the drive. But for kW, as we discussed before, you have a kW, but because of the difference of cosine phi and efficiency, actually the current is different. Is different, or you cannot decide, before you have a dedicated motor. So why still use kW? This is a kind of for the only reason is to make the customer much easier to size the drive according to the customer like to size the drive according to the motor kilowatt. Perhaps they don't have the data for the efficiency and the power factor. They just know the kilowatt. So actually, this kind of a guideline is first introduced by the Japanese company when we promote the low volt drive. So, for example, here 6 kV, and if you have a motor is 200 kilowatt, then you have a drive type of this drive type. But this is we have assumption this this is for the standard 4-pole induction motor, which means we will take the into account of the, for example, the cosine phi will be 0.85 and the efficiency will be 95%. We will use this as a reference, and then with the kilowatt and these two data, you can get a current of 26 amperes. Okay. So actually, the accurate method to size the drive is by current, not by kilowatt. Kilowatt is only for easy selection for the standard 4-pole motor with this roughly, this kind of efficiency and cosine phi. Also, for example, if the motor is 200 kilowatt and this is 16 poles motor, then for this special motor, the cosine phi will be much lower, maybe less than 0.7 or even lower. Then actually the current will be higher than 26, maybe over 30 amperes. So you cannot select this 16 pole motors with this kind of guideline. This drive, although the motor of the power rating of the motor is still 200 kilowatts, but the current is much higher than 26. So maybe you need to size this one. Okay, this current may be enough. So this is all for today's section. Thank you. Bye.